Hello everyone, my name is Namrata Ghag and I welcome you all for the video streaming of Ansys Workbench. Ansys Workbench is a CAE software which we are covering for 80 hours, and during these 80 hours we will be covering all the topics that you are seeing on your screen now. We will be starting with the introduction of CAE, and then we will enter into the software and understand the software capabilities for creating the models and for analyzing them using the different types of analysis that are there in the software. So let us begin with the first chapter, that is Introduction to CAE. In this chapter, we will be understanding what is CAE, the basic concepts that are involved in CAE, what is FEA, what are the advantages and disadvantages of FEA, what are the types of analysis that can be performed, and also some of the important definitions that are there in FEA. So let us start. What is CAE? CAE stands for the Computer Aided Engineering. It is the use of a software to simulate performance in order to improve product designs or assist in the resolution of engineering problems for a wide range of industries. What does this mean? We will be using the software for analyzing the designs and improving the designs. CAE software also includes simulation, validation, and optimization, which means that we can simulate our designs by analyzing it. We can also validate our design. That means when we analyze the design and we understand that there are some problems in the design, there are some mistakes that are there in the design, we will be validating it. That means we will be correcting our designs so that we don't scrap the design. We will be involving in the correction of the design also. And then also we can also be perform the optimization procedures to achieve better designs. Now, why should we use CAE softwares? Whatever products we are designing, they have to be according to the customer requirements. Hence, it is very important to analyze the design to understand whether the design is performing according to the customer requirements or not. What are the benefits of CAE? If we use the CAE software, it helps us make better decisions regarding the designs, material, and other economic factors. It also enables us to maintain standards throughout the designs and manufacturing. The use of CAE software also helps us to reduce the product development cost and time while improving the safety, comfort, and durability of the components that we produce. What are the application areas? CAE can be used in different fields like aerospace, automobile industries, energy, heavy machineries, marine industries, medical areas, consumer products, and many more such. Now let us discuss about another important concept that is involved in CAE, that is FEA. FEA is the study of behavior of components in real-time conditions in CAE that is achieved through finite element analysis. It is a computing technique that is used to obtain approximate solutions of boundary value problems. It uses a numerical method for in this, which is called as FEM, that is nothing but finite element method. Now let us understand what exactly is FEA. For this, what we will do is we will consider a small example where we need to find out the area of this circle. Now for calculating the area of the circle, we will not use the formula that is pi r square. We will be using a different technique. Now what is that technique? Let us divide the circle into 4 triangles. If you see on your screen over here, you can see that I have divided the circle into 4 segments and then connected these lines over here so that it forms a triangle. Now we will find out the area of one triangle and then sum it up so that we get the area of the circle. But in this case, you will see over here that this area is left out. So this is the error that I have got in the solution. So to reduce that error in my solution, we will go to the second step where now instead of 4 segments, I have divided the circle into more number of segments. Now as we have increased the segments, the area of error, if you see, the area of errors has now reduced. With this, we will understand that if we divide the circle into more number of segments, the accuracy will increase. But with more number of segments increase, the time required for calculating the solution is also increased. So the same concept we can apply in FEA, that is, if we want to have a better solution in FEA, we need to have more number of elements or more number of divisions. But if we divide the object into more number of elements, we will also have to spend more time in calculating the answer. So FEA is a compromise between accuracy and speed, but the compromise between speed and accuracy makes it an approximate method. Earlier, FEA was only developed to analyze the products that were used in the aerospace industry. But nowadays, you will see that FEA is used in all the industries and it is used for analyzing all the designs that we are creating. Now, when we talk about an engineering problem can be solved in three different methods, that is, experimental method, analytical method, and numerical method. What is that experimental method? Now, experimental method is nothing but it uses a prototype of the actual model and it is then tested under the real-time conditions so that we understand how the design will behave in the real-time conditions. This method gives us the most accurate results, but it is very costly and time-consuming. The second method is analytical method. Analytical method is actually very difficult, but this provides very accurate solutions. Now, you must have heard about the Rayleigh-Ritz method and the partial differential equations. They are actually examples of analytical method, but you know how complex it gets when your design gets more and more complicated. The equations will also get more and more complicated, and hence it takes a very lot of time to analyze the solutions. Third method is the numerical method. Nowadays, numerical method has become very popular for solving the engineering problems. The numerical method gives the most approximate results, but still it is used in many areas, and it will be using methods like finite element method, that is FEM, boundary element method, volume element method, and so on. Now, to understand more about the analytical method and numerical method, we will be considering one simple problem. If you can see, there is a small problem on your screen right now. We will be solving this problem using both the methods, that is the analytical method and the numerical method. Now we have one stepped bar over here. The cross section of the stepped bar can be anything. It could be circular, rectangular, or any other shape. And this stepped bar is subjected to a load over here. And the lengths of the step bars are also given, and A1 and A2 are the areas of the cross section. So let us understand this now. How to solve this using analytical method and the numerical method. Okay, so if you see over here, this is the same problem. You can take down the data over here. P, that is the force that is applied on the step bar, is 200 newtons. Area 1 is 200 millimeter square. Area 2 is 100 millimeter square. Length of the step bar is 100 millimeters for each of the step bar, and E, that is the Young's modulus, is 200 GPU. And we are supposed to calculate the stress induced in this step bar. So the first method that we will use is the analytical method. Now, in the analytical method, the first formula that we will consider is, if I need to calculate the stress, I know the formula for that, that is P upon A, that is force upon area. For calculating the strain, we know the formula, that is change in length upon the original length. Now, Young's modulus is stress upon strain, that is, you can consider this formula if you consider the Hooke's law, that is, the change in length is within the elastic limits, means when the force is getting applied on that step bar, when we apply the force on the step bar, it will undergo some change in length. But if I remove the force, it will regain its original shape. That means the deformation that we will get is within the elastic limits. Hence, It follows the Hooke's law, and we can consider this equation over here, that is E is equal to stress upon strain. Now, according to this, if we simplify this equation, we will see that stress is P upon A and multiplied by L upon dA. Now, let us solve this equation. So, if I take change in length on one side, the equation becomes PL upon AE, that is force multiplied by original length upon area into the Young's modulus. Now, let us calculate the change in length for the first bar. So, the formula becomes P into L1 upon A1 into E. So, if I enter all the numerical values, the change in length in the first bar is 0.5 multiplied by 10 raised to minus 3 millimeters. Similarly, let us find the change in length in the second bar, that is DL2. Again, if we enter all the numerical values, we will get the change in length in the second bar is 1 into 10 raised to minus 3 millimeters. Now we have got the change in length in the first bar and the second bar. So let us calculate the strain. So strain in the first bar is change in length in the first bar upon L1. That gives me 0.5 multiplied by 10 raised to minus 5. It is a unitless quantity. Similarly, strain into the second bar is TL2 upon L2, which is 1 multiplied by 10 raised to minus 3 upon 100, which is equal to 1 into 10 raised to minus 5. Similarly, we will calculate the stress in the first bar and the second bar. So, P upon area 1, P upon area 2, that is 200 upon 200, that is stress in the first bar is 1 Newton per millimeter square, and stress in the second bar is 200 upon 100, that is 2 into 2 newtons per millimeter square. Now let us move to the next method, that is the numerical method. In numerical method, we will be considering the same problem that we considered for the analytical method. Now if you can see over here, it's the same step bar that we have. We have area 1, area 2. The load applied on the step bar is P, and the length of the step bar is L and L. Now this step bar model that we have, we will convert that into a free body diagram. Now when you convert that diagram into a free body diagram, you will notice that I have marked something called as N1, N2 and N3 over here. Now N1, N2 and N3 is nothing but the nodes which connect the two bodies over here. That is the first body and the second body. Now let us start with the numerical method. Now at the starting of the numerical method, we will first consider the elastic behavior of a linear spring equation. If you can see over here, we have drawn one linear spring whose stiffness is K. The load applied at this point at the end of the spring is P, because of which there is a change in length that is called as dl. So if you consider the linear spring equation, the equation states P is equal to KdL, where P is the force applied, dl is the change in length, that is the displacement, and K is the stiffness of the spring, that is the spring constant. So if you take K on the opposite side, you will see the equation becomes K is equal to P upon dl. Now we also know from the previous solution that we've done for the analytical method, E is equal to stress upon strain, that is, if it is within the elastic limits, that means if it follows the Hooke's law. So our equation becomes P upon A into L upon dl. So now if we simplify the equations, our equation becomes P upon dl is equal to AE upon L. That becomes equation number 3. So if we compare equation 2 and equation 3, our equation can become K is equal to AE upon L. Please see carefully what we have done over here. Okay. Now we will be assuming applying the Newton's third law for the reaction forces. Now first we will consider the first step bar. Okay. So if we apply the Newton's third law of the reaction forces for the first bar, we will apply force at I, okay, we will be applying force at I and we will be locking J. That means I will be applying a force over here at the I node and we will lock the J node. If we do that, we will get an equation of stiffness, that is K1 is equal to K1. I am writing K1 because we are considering this in the first part, and K1 becomes, we are writing a stiffness matrix equation for the first step bar. It becomes A1 into E upon L. So the reaction for this is minus AE upon E, minus A1E upon L. Similarly, minus A1E upon L and A1E upon L. We are getting this by the Newton's third law. Every action has an equal and opposite reaction. Due to this, we are writing this equation. Okay. So this we have assumed for the first bar. Similarly, we are going to make a similar assumption for the second bar. So now what we are doing is we are applying force at the J node and we are locking I. So if we do that, now this is going to happen for the second bar. Okay, we are doing this for the second bar. In the second bar, we are applying force at J and we are locking I. So the stiffness equation becomes like this: A2E upon L minus A2E upon L minus A2E upon L, A2E upon L. Okay. Now I am going to calculate the global stiffness matrix. So global stiffness matrix is K, which is equal to K1 plus K2. So we have to add both the stiffness matrix. So now by combining both the stiffness matrix, that is K1 plus K2, you get this global stiffness matrix, that is K. Okay, so I have directly solved this and we get this global stiffness matrix. You can solve the same thing in your notebooks. So this over here is the global stiffness matrix that we have got. Now let us see what are the properties of a stiffness matrix. K stands for the stiffness matrix. So every stiffness matrix has some property. Now what are these stiffness matrix properties? If you look at a stiffness matrix, it will always be a square matrix. That means the number of rows and the number of columns will be equal. It is always a symmetric matrix along the diagonal. So if you take any diagonal over here, if I take this as the diagonal, you will see that it is symmetric above the diagonals. Can you see? If I take this as the diagonal, again it is symmetric. The algebraic summation of any row or any column is 0. If you add up any row or any column, the answer that you will get is 0. You can check the same for yourselves. The stiffness matrix always and only contains the geometric and material properties of the problem. If you look at the constants A1, E, L, A1 becomes the geometric property, L also becomes the geometric property, E becomes the material property. Apart from geometric and material properties, it does not have any other property. So that is why the statement that the stiffness matrix always and only contains the geometric and material properties of any problem. Okay, now let us go forward. Now we will put in the numerical values that we considered for analytical method. We will be considering the same values, and let us put all these numerical values in the global stiffness matrix and let us solve this equation. So my equation becomes something like this: 200 into 2 into 10 raised to 5 upon 100 minus 200 into 2 into 10 raised to 5 upon 100, 0, minus 200 into 2 into 10 raised to 5 upon 100, 200 into 2 into 10 raised to 5 plus 100 into 2 into 10 raised to 5 upon 100 minus 100 into 2 into 10 raised to 5 upon 100, 0, minus 100 into 2 into 10 raised to 5 upon 100, 100 into 2 into 10 raised to 5 upon 100. So we've got this by putting in all the numerical values in this equation. Further, we will solve it. Now what we have done is we have taken 10 raised to 5 outside and we have solved the equation. So our equation becomes 4 minus 4, 0, minus 4, 6, minus 2, 0, minus 2, 2. You can check this by solving this equation in your own notebooks. Now, again from the linear string equation, which we considered at the beginning of the numerical method here. So if we consider the same linear string equation here, okay, KDL is equal to P. But in this case, we have put them into brackets to show that this is a vector quantity and even P is a vector quantity. K is our stiffness matrix. Phi over here stands for the change in length and P over here stands for the force applied. So, if I consider the free body diagram, that is N1, N2 and N3. So the change in length, we will have different change in length at every node. That is, I will have a change in length at N1, I will have some change in length at N2 and I will also at N3. So if we consider the load applied at N1 is P1, load applied at N2 is P2 and the load applied at N3 is P3. Similarly, the change in length at node number 1 is phi1, the change in length at N2 is phi2, the change in length at N3 is phi3. So now we will be putting this into a matrices format. So stiffness matrix, whatever value we have got, 10 raised to 5 into matrices format, 4 minus 4 0, minus 4 6, minus 2, 0 minus 2 2. Change in lengths into the matrices format, we have written it as phi1, phi2 and phi3. Similarly, load acting at all the three nodes over here, P1, P2 and P3. Now, because node number 1 is completely fixed, the degrees of freedom over there are 0, there will be no change in length. That means phi1 will be 0. So, because in the matrices format, when you are multiplying two matrices, if any row or any column becomes 0, we can cancel out the entire first row and the first column. So now my equation becomes 10 raised to 5, 6 minus 2 minus 2, 2, phi 2, phi 3 is equal to P2, P3. Why we have done that? Because phi 1 becomes 0 as there is no change in length at node number 1. Now further, we will convert this into a simultaneous equation. So let us open up the equations. My equation now becomes 10 raised to 5, 6 phi 2 minus 2 phi 3 is equal to 0. That is P2 0 and 10 raised to 5 minus 2 phi 2 plus 2 phi 3 is equal to 200. That is P3. So now we will solve the simultaneous equations. So now my simultaneous equation becomes something like this. 4 phi 2 is equal to 200 upon 10 raised to 5. Phi 2 is equal to 200 upon 4 into 10 raised to 5, which becomes 0.5 into 10 raised to minus 3 mm. So now I have got the value of phi 2. We will calculate the value of phi 3. So if you substitute the value of phi 2 in any equation, you will get the value of phi 3, that is phi 3 is equal to 1.5 into 10 raised to minus 3 mm. So phi 1, phi 2 and phi 3 are the change in lengths at the different nodes N1, N2 and N3. Now from these values we will be able to calculate what is the change in length in the entire bar. So for getting the change in length in the first bar, our equation becomes phi 2 minus phi 1, that is dl1, change in length in the first bar. So now my equation is phi 2 minus phi 1. Phi 2 we have already got it as 0.5 into 10 raised to minus 3 minus phi 1. Phi 1 becomes 0. So my answer is 0.5 into 10 raised to minus 3. Similarly, dl2 that will become phi 3 minus phi 2. It becomes 1.5 into 10 raised to minus 3 minus 0.5 into 10 raised to minus 3. So my answer is 1 into 10 raised to minus 3 mm. From DL1 and DL2, we will be getting the strain values, that is change in length upon L, that becomes 0.5 into 10 raised to minus 5. Strain in the second bar is 1 into 10 raised to minus 3 upon 100, which is 1 into 10 raised to 5. So now we've got both the strain values. Similarly, we can also calculate the stress values, P upon A, area 1, P upon area 2, that is 1 Newton per millimeter square, and stress in the second bar is 2 Newton per millimeter square. Or else you can also use this equation to solve the stresses in the first bar and the second bar. Now if you notice, whatever answers we have got here are the same that we got in the numerical method. Sorry, the analytical method. See, so from this we can understand we have used two different approaches to solve the same problem. One was the analytical method and the second one was the numerical method. But the answers that we got using both the methods are similar. So with this, you must have understood what is a analytical method and what is a numerical method.